Yeah, we can go ahead and get started, Shreya. And if any other students pop in, they can pop in and out as they please.
All right. So, hello everyone. My name is Shreya Jaiswal, and I'm a graduate student. I came in fall 2022 for Masters in Information Systems. And yeah, so today I'll be giving a very brief overview of a little bit introduction about what machine learning is. And I'll be emphasizing mostly on the supervised learning and the linear regression part. And I've tried to made it interactive uh, with few videos and like try to make it visually uh, appealing so that it's very understandable. So at any point of time, if anyone has any questions, please do stop me and feel free to ask your questions. So just to start off with, this is a brief overview of what I'll be going through today. So we'll be starting through the introduction to machine learning and supervised learning, followed by linear regression. And then I will be referring to a particular case study. And based on that case study is where I'll be going through the different terms, like how supervised learning is used for that particular case study. And the same case study we'll be using and going through the code as well. And then a little bit about my coursework, which I did last semester. I'll be talking about that. And then we'll go through a little bit of statistical learning and the differences. So most of the time, what we see, like when we hear about machine learning, we get very intimidated because it's mostly about statistics and it's about mathematics. Not everyone feels comfortable trying to learn, okay, fine, or what it is, or how do we go about it. So even I was like that in the beginning. I was actually very scared. I was like, oh, it's full of maths. How am I going to do? But eventually, when I started like reading and understanding, like taking one topic, say for example, if I'm starting to learn supervised learning, I take that particular topic and then I just tried understanding what that is and then how that is implemented. So it is very uh, easy to understand when you have your mind open and when you are willing to uh, take, like you're willing to understand and not scared to learn, basically. So to start off with, I have a small video just as an introduction to the machine learning part. So let's just start. Yeah.
We know humans learn from their past experiences, and machines follow instructions given by humans. But what if humans can train the machines to learn from their past data and do what humans can do and much faster? Well, that's called machine learning. But it's a lot more than just learning. It's also about understanding and reasoning. So today, we will learn about the basics of machine learning. So that's Paul. He loves listening to new songs. He either likes them or dislikes them. Paul decides this on the basis of the song's tempo, genre, intensity, and the gender of voice. For simplicity, let's just use tempo and intensity for now.
Okay. So before we move on to Paul and understanding this particular case, so what this video just told us very nicely in the beginning, what is machine learning? So machine learning is nothing but reading the past data in order to understand what the future data is going to be like, right? So we can, like the most basic example we can think of is, say, our grades, right? We invest our time, we invest our resources in order to learn something, and the end result is so that we get good marks, or say we score well in that subject, right? So now if a particular professor has been teaching for a span of say 10 or 5 years, so we can understand that the amount of data collected by the professor every year, like based on the students, can actually be helpful to determine what kind of a student would score what marks in his next 5 years. So machine learning is basically trying to understand the past data, and there is a processing which happens in between, which we'll talk about, in order to understand what our future data is going to look like. So in this particular case study, we are going to see how Paul likes or dislikes a particular song based on different factors. So the factors are as
So
follows in the
here,
video.
tempo is on the x-axis, ranging from relaxed to fast, whereas intensity is on the y-axis, ranging from light to soaring. We see that Paul likes the song with fast tempo and soaring intensity, while he dislikes the song with relaxed tempo and light intensity. So now we know Paul's choices. Let's say Paul listens to a new song. Let's name it as Song A. Song A has fast tempo and a soaring intensity, so it lies somewhere here. Looking at the data, can you guess whether Paul will like the song or not? Correct. So Paul likes this song. By looking at Paul's past choices, we were able to classify the unknown song very easily, right? Let's say now Paul listens to a new song. Let's label it as Song B. So Song B lies somewhere here with medium tempo and medium intensity.
Okay, so what we saw in this particular scenario is that we are trying to find out what kind of song Paul likes. So, and how we're going to find that out based on two factors: the tempo of the song and the intensity of the song. So if the tempo is slow, that's usually something which is like more of a relaxed and a calm song. And if tempo is high, that's more like, of a party, or it's like the pop kind of songs, right? So here we see that as most of the songs which Paul likes is towards the faster tempo side. So in future, if there is a new song which is released and which meets the factor,
Neither
which meets these factors, then we can say that, yeah, this particular new song is of more interest to Paul. But if say that there is a comparatively less and a relaxed and a calm song which is released, then that would probably not be of Paul's interest. So this is what machine learning looks like. It tries to understand what kind of song Paul liked before, and based on that, what he's going to like in future. So we spoke about one of the kind of songs which he could like. Now let's see what happens if there is a song which it's neither relaxed nor fast. What happens to that song? Does Paul like it or not? Let's just have a look at it.
relaxed nor fast, neither light nor soaring. Now can you guess whether Paul likes it or not? Not able to guess whether Paul will like it or dislike it? Are the choices unclear? Correct. We could easily classify song A, but when the choice became complicated, as in the case of song B, yes, and that's where machine learning comes in. Let's see how. In the same example, for song B, if we draw a circle around the song B, we see that there are 4 votes for like, whereas 1 vote for dislike. If we go for the majority votes, we can say that Paul will definitely like the song. That's all. This was a basic machine learning algorithm also. It's called K-nearest neighbors. So this is just a small example in one.
Yeah, so here what we saw that the song B was neither close to the relaxed one, nor was it totally clustered with the fast tempo songs. It was somewhere in between. So in that case, we saw that particular song is close to what kind of a genre or what kind of tempo? Was it more towards the relaxed part, or was it more towards the fast tempo part? So as told in the video, we see that it is more close to the ones which have a faster tempo. So it's more likely that this song will be of Paul's interest. So what this entire scenario or the case study was trying to tell is, based on a very few number of past songs that Paul liked, we could determine his future songs. So you like, I think we can relate this with the current recommendation systems which are used. So on Netflix or even on YouTube, if we go and if we start liking songs, we see that after a while we start getting recommendations based on the ones which we've liked before. So how does that happen? So this is something close to that. It's because it reads, it understands, and it groups our likings, and based on that it recommends what we would like in future. So this was about a very simple example of Paul liking the song or not. So this was just an introduction of machine learning and what exactly it is. Any questions for like till now, please feel free to ask. Okay, so I'll be moving forward with the next part. So most of the time we hear artificial intelligence, machine learning, deep learning. And at the beginning, when I used to hear these three terms, I used to be like, okay, wait, what is machine learning? Is it a part of AI, or what is AI? Is deep learning part of AI or machine learning? What is it? So I think this Venn diagram very nicely explains how these three things are interrelated, as well as how they are distinguished from each other. So we see that machine learning is part of artificial intelligence, where it is a subset of AI. And so machine learning is heavily dependent upon the data which we already have. So that's the reason why we emphasize on having a historical data or having a lot of data. And in today's world, I think people are talking about data breach, they're talking about data security. Why are they talking about all these? It's because data is very important. It is important because that is what is going to determine what their future business will look like. So machine learning is part of the artificial intelligence, and deep learning is part of machine learning. So I won't go in detail about what deep learning is, but what I can tell is deep learning is more of dealing with more layers and more learning. So if we can visualize how our brain works, right? So our brain is a network of neurons. So they have the concept of perceptron comes from the way our brain functions. So we look at something for the first time, we don't know what it is. For example, we know orange as a fruit, right? And what if tomorrow a mango, which looks close to an orange, comes? Our brain will be like, okay, fine, wait, is that an orange, or is that some new fruit? Or so that's exactly what the machine learning algorithm at the first looks like. If you give a new information, it'll be new to it. But eventually, if you keep feeding it with the data, it's going to understand the data, group the data accordingly, and then it's going to make sense out of it. So let's move on to the types of machine learning. So there are basically three primary types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. Before I move in detail about all these these three types, let's just hear
Hello,
about
everybody.
this case study.
Hello, everybody. My name is Mark and I'm currently working at a health insurance company. Before Shreya dives deep into the types of machine learning, I would like to tell you guys about the current project my team is working on. Before I tell you guys about my project, I would like to talk a little about what health insurance means. Health insurance is a means of protecting oneself from financial losses due to medical expenses. It typically covers the cost of medical treatments, hospitalization, medications and other factors. The cost of health insurance premiums varies based on factors such as age, gender, pre-existing medical conditions, and geographic location and many more factors. Let's talk about the project my team is working on. Well, we have been given a dataset containing the information about our clients. This dataset includes client information such as age, sex, BMI, number of children, whether the person smokes, region, and the charge our clients pay for their health insurance. Our goal is to create a precise model that predicts health insurance costs based on factors like age, gender, BMI, smoking status, and more. By leveraging this model, we can anticipate future charges for our valued customers. Shreya, now you can take on this exciting case study and explain how machine learning is implemented in a straightforward way.
Okay, so this is going to be a case study throughout the next few minutes, which I'm going to be emphasizing on, so that we do not divert into many aspects, one particular application, and trying to understand how the terms of supervised learning, machine learning work for this particular case scenario. So we heard Mark, he spoke about a project about health insurance. So basically, this is a data set containing, this is my data set. So this usually we find it in a form of Excel. I have just embedded it in this page so that it'll be easy for reading it. So my data set contains these columns. So we can see that we have age, we have the sex of the customer, the BMI, the children, number of children the person has, the client has, this, whether the person smokes or not, the region the person belongs to, and the charges. So this is fairly a very small data set. It has very limited number of columns, but usually when we deal with the real data, the number of columns are a lot. So we usually call these columns as attributes. They're also known as features. So I will be using these terms interchangeably. So please do not get confused. So most of the time we call them as features because we are going to use these features to predict some response. So here, what according to you guys do you think we should be predicting out of these columns? Okay, let me just, yeah, sure. This is the column present in my data set. What according to you do you think we need to predict? Like, I think you guys can just tell any column and we can have a discussion on why do you think so. Okay, so here we see that this particular column is the charge a particular customer would have to pay for his health insurance based on the different factors, right? So we see that these are the charges. So according to Mark, he said he wants to find the charge his future customers would have to pay based on these factors. So he wants to predict a model which can help his customers out that see in the next 4 years or 5 years down the line, if your BMI is this, if you are a person who smokes, then you'll have to spend so much on your health insurance. So our response variable here is going to be charges. So charges is my response variable. And how are we going to predict the charges is going to be based on our different column values or features, as I said, such as the age, BMI, smoke, and the region. So these are called the predictors. So now what we see here is response is a numerical value, right? And we know what we are going to predict. So now, since we already have it labeled, this particular kind of machine learning is what we call as a supervised learning. So supervised learning is when our data is labeled, we know what we are going to predict. It can be quantitative, it can be qualitative. So when I'm telling it can be quantitative, I mean that it can be a numerical value. Like for example, charges. So charges is a numerical value, it is continuous. So it is giving me some quantitative value, right? So when we are dealing with supervised learning and when we are dealing with the output, which is continuous and quantitative, we usually go for the regression algorithm. So regression can be defined in multiple ways. So it can be linear regression, it can be multilinear, it can be polynomial. We'll be sticking to linear regression, and for this particular case study, multiple linear regression. So I'll be talking about more about the linear regression part, but just for you to understand what kind of learning this is. So this is a supervised learning. And why is it supervised learning? It's because we have our response, what we're going to find out, what we're going to predict. We know what we're going to predict. It is a label. It is not something which we do not know. So anything that is labeled output and that we're going to predict is known as supervised learning. So this is a quantitative learning and it is continuous. Now, there can be other kind of labeling as well, which is not quantitative. For example, say if I want to differentiate between a cat and a dog, right? So that is not something which is numerical. That is not something which is quantitative. That is more of a qualitative response. You either, it's a categorical data where you categorize whether this particular image is going to be cat or whether this particular image is going to be dog. So this also is supervised learning because we know what we are going to classify our future input as. So primarily supervised learning are of two types. Again, so for classification, we use logistic regression. We won't be going too deep into the math or the concept of logistic. We'll be sticking to linear regression. But just so that you understand what supervised learning is and how quantitative is different from qualitative is why I had given this example. So is there any question related to supervised learning or what is supervised learning and difference between classification and regression? Please feel free to ask. Okay, so let's move on to the linear regression part. So as I said, this particular data set just has it has just 7 columns, right? And I deliberately took this kind of a data set so that we could understand how columns deal with predicting the response that we are looking for. So here, age, we can consider that to be our predictor variable. Predictor variables are also known as independent variable. Then all my first 6 features or my first 6 column are my predictor variable or independent variable. My charges, which is y, is my response variable. Now, response variable is known as dependent variable because the value of my response is dependent on all these factors. It's dependent on the age of the person, then whether the person smokes or not, which region the person belongs to, the body mass index of the person, right? So that's why charges is a response variable. Now we are moving on to the mathematical part because I feel just by running the commands on Python, it's no point if you don't know what is happening behind the scenes. So having a little idea of how the linear regression works will make a lot of difference in terms of understanding or even, trying to see how the response or independent and the dependent variables are related with each other. So this is a video just to I thought I'll play this if not many of you are aware of the linear regression part, or if you're not, then I'll just proceed explaining. So do you want me to play the video to make you understand what are the linear equations and how the variables are dependent or not? I mean, those who want me to can just, I think, put a heads up or anything. So I'll just. Let me just play this then.
What I'd like to introduce you to in this video is the idea of a linear equation. And just to start ourselves out, let's look at some examples of linear equations. So for example, the equation y is equal to 2x minus 3. This is a linear equation. Now, why do we call it a linear equation? Well, if you were to take the set of all of the xy pairs that satisfy this equation, and if you were to graph them on the coordinate plane, you would actually get a line. That's why it's called a linear equation. Let's actually feel good about that statement. Let's plot some of the xy pairs that satisfy this equation, and then feel good that it does indeed generate a line. So I'm just going to pick some x values that make it easy to calculate the corresponding y values. So if x is equal to 0, y is going to be 2 times 0 minus 3, which is negative 3. And on our coordinate plane here, we're going to move 0 in the x direction, 0 in the horizontal direction, and we're going to go down 3 in the vertical direction, in the y direction. So that's that point there. If x is equal to 1, what is y equal to? Well, 2 times 1 is 2 minus 3 is negative 1.
Okay.
So we move positive 1 in the x
Let
direction
me pause
and
this here.
negative 1 or down 1 in the y direction. Now let's see, if x is equal to 2, what is y? 2 times 2 is 4, minus 3 is 1. When x is equal to 2, y is equal to 1. And hopefully you're seeing now that if I were to keep going, and I encourage you to, if you want, pause the video, try x equals 3 or x equals negative 1 and keep going, you will see that this is going to generate a line. And in fact, let me connect these dots and you will see the line that I'm talking about. So let me see if I can draw. I'm going to use the line tool here, try to connect the dots as neatly as I can. There you go. This line that I have just drawn.
All right. So, okay, there was some issue. I was not able to pause it.
What I'd like.
But
So
what I wanted to convey from this particular video is just a basic understanding of the equation of line y is equal to mx plus c, right? So here, what I'm trying to tell is y is the response variable. In this case, we will consider our y to be charges. I'll be moving on to that equation below. So this particular is just a linear regression equation. So we see there's just one independent variable and there's one dependent variable. So the independent variable is my x and my dependent variable is my y. So for example, I just wanted to find the charge my particular client wanted to pay based on his BMI. Then that would be just a simple linear regression problem where I am dealing with one response variable y and one independent or predictor variable, which is BMI. So in that case, what would my my equation would look like? Y is equal to B naught plus just B3 into BMI. I wouldn't have had any of the other features here. But in our case, we are trying to predict our charges based on multiple independent variables. So this is more of a multiple linear regression problem. So why? So this particular equation is for a multi-linear regression problem where we have one response variable and we have multiple independent variables. So x1, x2, x3, x4, x5 are nothing but my predictor variables. Based on what am I going to predict my response, right? So here we can substitute our x1 with our variable. We can, so the charge my client has to pay would be based on how old or young is that person, whether the person has a higher or lower BMI, the number of children the person has, whether the person smokes or not. So these are the factors which are going to help me determine my response variable. Now, our entire equation can be reduced to the one which we see below, right? So f of x is nothing but the function which we obtain from our independent variables alone. And when we hear about predicting models, training models, so this model is nothing but this particular function that we're trying to find, right? We're trying to find the best possible model or the function which helps us get nearest to the accurate value. So this is a very basic and a very general overview of how a multiple or even a simple linear regression works on. So any question based on this particular concept which I just explained? Okay, so I'll be moving forward with explaining the same thing using my Google Colab notebook. So this is more of a practical based learning. I think it'll be more helpful in visualizing and helping understand what it is. So this is my Google Colab notebook. I usually prefer to write it along with text because what I feel is when we are learning something, it's good that we also make note of what we are learning at that point. so that when we have to go back to that same thing, right? So it'll be easy for us to relate and understand. So since this entire thing was based on linear regression, I have made notes on what types of linear regression did I work on. So as I was explaining, there are two types. There's simple linear regression and there's multiple linear regression. And simple linear regression deals with just one independent variable, as I had mentioned before. So this is what the equation would look like for a simple linear regression. Then for a multiple linear regression, again, it will have multiple independent variables. So this is what the equation would look like. There are certain metrics which we deal with in order to see how good our model is. So the statistical metrics that I had worked on was mean square error and the variance. I'll be talking about this eventually as we go through the code. But these are the two main statistical measures based on which we'll be telling whether a model is good or not. And okay, so just to make you guys understand what this equation is, it is not something very like it's not something which is out of the box. All of us can understand what this particular equation is, right? So I'll tell. So when we are predicting anything, right? So there is a past data which we take and train a model. Once a model is built, we use a future set of data, a new set of data to predict whether what we have trained our model on, is it predicting the right thing or not? So usually, I'm sure all of you would have come across, splitting the data into training data and testing data. So why do we do that? We do that because using the training data, we can develop a model, but test data is the one which helps us validate whether our model, which is built using the trained data, is accurate or not, or is it even close to what we are expecting or not. So when we try to find our prediction based on our training model, then we get the response variable, right? The predicted value. And it is obviously not possible. The ideal scenario would be to get the exact response, but that is not the case because a model takes time to understand the data, and more the data, the more better the model is. But that's a very ideal scenario to get the exact output. So yi minus yi cap is the difference between my actual value and what my model has predicted. And our target is to reduce this difference. Lesser the difference, that means more close my predicted and my actual value is. And that is what we want, right? So yi minus yi cap. Yi is my actual value, yi cap is my predicted value. And we are doing the square to basically cancel out the negative and the positive variables. We just need the magnitude. And n is the number of data the number of rows and the amount of data present in my particular data set. So it is just a very simple and a basic formula. And it is mean squared error. The aim is basically we have to reduce our mean square error to get a good model. So that's the basic idea. Again, variance is how far your value is from the actual. So before I explain variance, there was a very nice explanation which is given on this that I will share these references with all of you. So yeah. So when we're talking about variance, so usually we see, right, we tend to talk about the normal distribution. Why is normal distribution required? So the normal distribution is basically, we do that so that our data is in a right scale, right? If we have different scales of different data, then obviously the model which is going to be predicted based on this data is not going to give us a good result. So there has to be a proper definition, there has to be a proper scale so that there is uniformity across the data that we're working on. So usually we see that, so these two types of two different normal distribution, right? Now, how is this different from that? If the curve on the top is shorter and wider than the curve on the bottom, because the curve on the top has bigger standard deviation. So more the standard deviation, that is more your value is away from the actual thing, it'll be wider. And the lesser it is, it'll be more sleek and taller. So we will see this in our, like when we are going to plot our graphs for this particular data set. So these two are the basic statistical measures that we'll be going through. So starting right from, yeah, so these are certain packages that I have installed. This is the library, right? So before starting off and training any data, it's very important that we have a uniform and we clean the data before processing it. So these are a few functions which I've defined, and these are just very basic functions to have the column names uniform. So as you can see, I have removed the extra spaces using the strip function, and I have replaced the blank spaces. I just wanted all my column names to be in lowercase, and I have used the camel case, like I've separated them using an underscore. This function too is about the null information basically. So the null present in my particular data set is what this function is doing. We'll be using this to find how many null value or how many missing values are present in our data set. This is equivalent to finding the null, but this is just in terms of finding the percentage of the missing values. This is not necessary. Residual plot. This is just plotting a little bit of visualization part which I've used. Yeah, so there is one thing which, so Python already has an inbuilt library, sklearn, which helps us to find these statistical factor measures. Like if you want to find the MSE, we already have a built-in function which gives us the MSE value, variance value. But in order to just understand it in a much more better way, I have tried to define my own function defining the formula, and then I've tested it using the inbuilt function just to see whether the calculation, which my understanding of the calculation, is it right and is it meeting with the same which the Python library is providing. So we'll be seeing that as well. So this is the data set which we were talking about. It's present on Kaggle. You guys can also go have a look on the data set. It basically has, as I said, 7 columns. Charges is our response variable, and these are the other features. And so here I'm reading my data set into the data frame. So this particular data set has around 1,338 row count. So that's the amount of data we're dealing with for now. And so we've started off with cleaning the data column names. So this particular function is what I had used initially. So using that function, I'm just making all my column names lowercase, and if there's any extra space which needs to be removed, it's removed. Then the next part is doing a little bit of ADA. So I'm sure all of you must have known what correlation is, right? So I'll just very briefly explain what correlation is. So correlation usually takes place between one variable, one independent variable, and one dependent variable. So for example, here, let's just talk with the example of charges. So here, charges is my dependent variable. It is dependent on age, BMI, children, etc. But now when I'm talking about the correlation, I'm trying to see, okay, fine, how is my age correlated to the charges? How is my BMI related to charges? So usually they are scaled from 1 to -1. That's the range. And if it is more close to 1, then we say it's positively correlated. That means with every increase of that particular variable, I will see my response variable increasing as well. Similarly, if it is more towards my -1 part, then that means it is negatively correlated, stating that with every increase in that particular independent variable, my dependent variable would decrease. So in this case, we see that age and charges have a moderate positive correlation. So, and it would also make sense because you can say indicating that older individuals tend to have higher healthcare costs. So if we just think logically, right, old people who are, older than, like they're towards their old age, they would probably have to take better care of their health and put more money and spend a little bit more compared to the ones who are younger to maintain their health. So similarly, people who smoke more, or the ones who are, the ones who tend to smoke more will tend to have higher charges paid for their insurance because obviously they are compromising on their health in the long run. So, so what we can see here is we can relate these numbers to the actual, actual scenario which happens around. Like we can relate it logically. We can actually see that yes, old people do require a lot of they need to take care of their health, and if that's the thing, then they would have to pay more for their charges. And thinking it that way would make it more it actually helped me understand more better in terms of the numbers and the application. So I always take application and numbers hand in hand so that that's the better way of seeing the problem and understanding it. The next EDA part, which I meant, is to check for the number of smokers, the ones who smoke more, and among them, we see that many of them do not smoke, but the ones among those who don't smoke, we see that the females don't, like the women don't smoke more, they smoke lesser than the men. And we can see the count likewise. Then the distribution of charges based on the BMI and the sex. So we see here as our BMI increases, like the BMI of the person or of the client, if it increases, so does the charges, right? So with increase in BMI, the charge is also increasing. And we see that it's more likely that the men tend to have a higher BMI and they usually have to spend more on the charges, which is spend more on the health insurance. So that's what this particular graph is telling. The next is the distribution of the people who smoke based on the region. And then we see that the Southeast region has the most number of smokers. So we can see that this particular region has people who smoke more compared to the other regions. And distribution of charges based on age. As I said, as people grow old, they need to take more care of their health, and eventually, so as a result, their charges of obtaining the insurance also increases. And this is just a distribution of charges with increased BMI for the males and the females. So we see that the male tend to have higher BMI compared to the females. We saw the same kind of a plot. I mean, we saw the same result for even this particular plot, right? With the increase in charges. So these are just two different kinds of plots. So this is a histogram one. The other one was a scatter plot. Then coming to pair plots. So pair plot, given a data set, pair plot will give us the visualization or the relation between every column value with every other. So here we see that we have around 7 features, 7 columns, and we can see the relationship of every column with every other column. So our main area of focus is charges with the others. So this is what we'll be looking for. Okay. Now, once we are done with the EDA, the next is data preprocessing. So a model will not be that good if if we have outliers or if we have null present, because that is not something which would make our data good or strong, right? So it's very important to clean and process our data before we even train it, because otherwise it will definitely affect in the prediction of our future information. So a good practice is to deal with the null values and to deal with the outliers. So in this particular case, we don't see that there is any null values present. We don't have any null values, and if we visually see, we see that, okay, I mean, our data looks good. So we can move forward with respect to the nulls. The percentage of nulls, again, it is 0. So we don't have any obstacle with respect to dealing with nulls in this data, at least. The next is the outliers. So usually what happens is, when we have our data, it's not very, in the real world, we can't expect our data to be uniform. There has to be variance across, right? So, but the target is not to have extreme values so that they tend to change our model completely. That is also bad, because then it's not going to help us determining the result of the future data anyways. So what we try to do here is we first see what kind of outliers are present. So usually there are different types of algorithms which are built to deal with the outliers. For this particular case, I've used the Tukey method. So basically what this method is doing is, so I have my interquartile range, right? So some amount, like the higher quartile range and the values above that range is what I'm trying to eliminate, because I don't want that. Most of my data resides in this range, so I'm going to focus only on this data. So that is what this method is doing. And okay, so one more interesting and important thing is one-hot encoding on categorical data. So if you remember in the beginning, I mentioned about supervised learning. It can be quantitative form and it can be qualitative form. So when we are dealing with linear regression, we see that the values are numerical and they are continuous. So if our response variable is continuous and if our response variable is numeric, we have to make sure that our independent variables are also numeric and continuous. So in this case, we see that the value of the column smoker is Boolean. It's either yes or no. But we can't just use that categorical value to evaluate our response variable. So in order to do that, we have to perform one-hot encoding. So what one-hot encoding does, it just changes the value to 0 or 1. So this is a binary classification, so it is easy for us to visualize it. And like you can see it over here, after performing one-hot encoding, instead of before it was yes, no, 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 no. But then after we performed, it is changed into a numerical value. And now it would be a better, it'll help us to better understand the response. So that's one-hot encoding is a very important pre-processing step before we train our model. So that is also equally important. Moving on to the feature engineering part. So QQ-plot is very extensively used across. So just to make you guys understand, so initially even I used to be very confused about what exactly does the QQ-plot tell? Why do we need to have the data normally distributed? And if the data is normally distributed, how do we expect the QQ-plot to be visualized? So I think this particular image talks about it. So if our data is normally distributed, then we see that our QQ plot is going to be fairly linear. If it is too peaked in the middle, then this is what our QQ plot is going to look like. If it is skewed, then we see that our QQ plot is curved. So this is the basic visualization with respect to the QQ plot. And so let's see how our data is with respect to these. So what we see is with age, the QQ plot of age is not exactly linear. It is something which falls in this category. It is not normally distributed. It does not look skewed. So it falls that data is peaked in the middle. So that's what we infer from this particular plot, right? Now, QQ plot for BMI is fairly linear. So we can say that, yeah, most of our data for BMI looks something like this, because the QQ plot is like, it's almost linear. Likewise, where did it go? Yeah. QQ plot for children. Children is again a categorical value. I mean, it's numerical. It's 1, 2, 3, 4. So we are not going to infer anything from that. Charges is what we have to gain. So that's our dependent variable. And smoker again is our binary. It's either yes or either no. So to understand the QQ plot in a more visualizing way, so this is what the histogram would look like. So I think this particular image, which I just had for comparison, talks a lot. So our histogram plot for BMI should look something like this. So let's see if it does. Yeah, so as we can see, right, the distribution of our BMI does look normally distributed. So that's how I think you're like, we can compare how our data should be for the QQ plot. And if it is not, then what are the other things that we need to do to make the data normalized? So in this case, I just use the min-max scalar again. And the min-max scalar is, again, there are a lot of different, you can use robust scalar, you can use min-max scalar to normalize your data. It depends. Sometimes maybe we need to try 2-3 different things to see which gives us the best model. I just went with min-max because that's the most widely and commonly used. So I just I use that to normalize the data again. So what min-max scalar does is it just fixes a range, as I said, right? It's very important that our data is in a particular range. Like say it has a range of 0 to 1. Like it should not be fluctuating, because if it is, then your model would not be based on any fixed scale. And if there is no fixed scale, then I don't think the model is something which is very reliable. So it is important to scale your data, normalize your data in that sense. So these are the coefficients after the data has been normalized. We will see how it looks visually, because I think that is more understandable. Yeah. So as you can see, histogram of age, BMI has become more fairly normalized. Histogram of charge is a little skewed, but that is what we're predicting, so it should be fine. And this is a binary classification again. Again, just trying to see the correlation here. Again, we are visualizing the pair plot. So here, what we see is, after normalizing, there has been like the correlation coefficients have had significant increase or decrease in their values. So we have plotted that again. Okay, so let's move on to the ordinary least square part. So this is a predefined function. Model.summary is something which already gives us a lot of statistical values. What I would focus on is R squared value. So our R squared value is basically, it tells how important our independent variables are with respect to determining what the response variable is going to be. It's in the scale of 0 to 1, with 1 being that yes, your independent variables are important to determine the response. So we see that here we have a value of 0.765, so which is towards 1, and so for now we can say yes, it is the model which is formed says that, you know, based on your features are important to determine whatever you're looking for. In this case, you're looking for charges. Now, this again, I would talk about the P factor, the F statistics, or the P value. So I'm not sure if you guys are aware of the null hypothesis and the alternate hypothesis to it. So what these hypotheses say is, null hypothesis says that assume that there is no relation, absolutely no relation between my independent and the dependent variable, right? So if my p-value is lesser than 0.05, 0.05 is considered is 0.05 is mostly considered as the standard value. That's what we choose, but it again depends on the value which the data you are dealing with. But till now I have used this particular value itself. So if my p-value is lesser than 0.05, that means this particular feature does have a significant impact in determining my response variable. So here, all the values we see are lesser than that. So all of them are fairly significant. So this is, in simple words, what the null hypothesis states. Like, it just tells that if my p-value is lesser than 0.05, that means these values are important in order to determine my response variable. So once we are done with all this, the next and the final part is where we build the model. So again, as I had mentioned before, we are training, we use train, test, and split. We use a certain amount of data just to train it, and the rest we use to test it. So distribution of the training data. Yeah, this part. So it's important that our distribution is fairly across all the records. It shouldn't be that, you know, the age of the data present in the training have the older ones, but we are testing just the kids or the younger ones, then our model won't predict it right. So it is important that our data in the training and testing is equally distributed throughout. So this particular visualization helps us see whether it is equally distributed or not. So we can see that, yeah, my training and the testing has all the data spread across. Similarly for BMI and children and the last column as well. This particular cell is just training that we're just fitting the model. And these are our coefficients that we have got. We are plotting it, but yeah. So this particular visualization on this particular table just shows us that which feature is significantly important in determining our response. So we see age plays a very important factor in determining the charge. Whether the person smokes also is an important factor which helps in determining how much the person has to spend in his health insurance. Likewise, BMI is at third, and then the last thing would be the number of children. Again, these are a few of the mathematical part which I kept adding on for my understanding, because it's easy, like for me to come and again look at this particular code. I just have to go and see, okay, fine, this is the concept which I used to form this particular function. So in the beginning, as I said, sklearn already provides a built-in function, but I just wanted to see mathematically whether this is working or not. So this is where I use the formula to find my mean square error. The mathematical formula for finding is this. And scikit function is using this particular built-in function to find the same. So here in the output, if you see, this particular value which I have obtained is using the mathematical formula which I defined, and this is from the scikit function, and both the values are same. So this kind of a practice help me also understand, okay, yeah, so this is how the function is used, and also in mathematical way, like dealing with numbers also, this is how it is used. Similarly, I tried this for variance as well. Variance, there was a slight difference, but I mean, it seemed to be close enough. So yeah. Well, let's talk about the test. Yeah. So here we finished training a model. We found the model. The next part was to plot the residual, right? So this particular line is what is the actual response that we want. This is like the perfect line, perfect model and the response that we're expecting. And the ones which are plotted here is what we are actually getting. So our aim is to reduce the distance between the plots and the actual line. So this particular distance here is nothing but my error, residual distance. And the aim of the entire building of the model is to minimize this error. So lesser the error, more close our model would predict it to the true value. So this is the end plot of it. And yeah, any questions with respect to any of the topics? This was a very simple example I used for determining linear regression, but overall this is the approach which is followed in order to determine. Any questions from anybody? Okay. I will be sharing these materials and my notebook also, if anyone wants to go through and see how it looks like. I'd be more than happy to share. These are few of my works, which last semester I had taken the data science course under Professor Nick Brown, and I think working under him was I mean, it was a lot of things that we had to explore on our own, but it was worth it, I feel. I did a lot of I explored a lot of APIs, and I tried to do something on my own. So this was one of the very recent things that I did, like just generated an AI generated arthritis data set. Let me just show this. Okay, I'm not able to open it. Let's do one thing. Okay, just give me a minute. Yeah, so I just created an AI generated arthritis X-ray images using prompt engineering. So professor usually keeps showing like using different already trained models. I think currently he's working on Midjourney. The one which I used was DALL-E, which is provided by OpenAI. So any questions regarding his coursework or like how the course is or anything related to that, please feel free to ask. Like I'd be more than happy to share and help any one of you at any point of time. Then my actual work was with regard to the life expectancy. You can find this particular article as well, where the way I explained today, it's just written, but today I was explaining more about the health insurance part. This particular article is more towards predicting the life expectancy, and this data set is a huge data set. So it has around 20 to 22 columns, and the same approach was used dealing with simple and multiple linear regression here again, but the features were more, and we were trying to predict what could be the life expectancy of a person based on so and so factors. So it's been explained in this article with the EDA, and yeah, so just you guys can go through, or if you have any interest or anything which you guys want, where I can be of any help, I'd be more than happy to help. That's it from my end. Any questions?
It looks like there's no questions. Well, Shreya, thank you so much for such an informative and well, I think, planned session. I know I learned a lot. I'm sure everyone else who attended today did as well. And just thank you so much again for your time and your efforts in creating this workshop for us.
Thank you so much for this wonderful opportunity, Kaylee. And it was a learning for me as well. But yeah, anytime if any one of you need any help or any kind of a thing, just reach out to me and just feel free to. Yeah.